Should I start? Okay. So thanks for the invitation. I have to admit, I don't work on conversational question answering per se, but I think this will be hopefully relevant for many of you. It's going to be a lot about synthetic data, and it has the title that you see here. So let's start with a case of scope ambiguity. So let's look at this sentence. There is a pre-training method for every NLP task. And there are two ways to interpret this sentence based on the quantifier scope, the existential and the universal quantifier. One possibility is when we say that, is that we mean that there exists a single pre-training method such that this pre-training method will be useful and will work for any downstream NLP task. That's interpretation number one. And if you switch the order of the quantifiers, then we are saying that for every downstream NLP task, there exists some pre-training method, not necessarily the same one, such that this pre-training method will be good for the downstream NLP task. And roughly 3 years ago, when BERT came out, at least in my head, it seemed that there is this promise that there is this one pre-trained model. It was expensive to train and so on. But now that we have it, now it's useful for everything, for every downstream NLP task. And that's great. But very quickly, people realized that maybe it's not exactly like that. So for example, there are many papers, this is not representative of the entire literature, on many things that are not captured by language models. For example, there was a paper on negation, and then there was some paper on multi-hop reasoning from my group by my ex-student, my alumni, Alon. And also on top of that, people quickly realized that if you know something about the class of downstream NLP tasks that you care about, you can maybe design a better pre-training method such that they will be closer. And if they are closer, then it will be better for the downstream application. Maybe it will require less data in the few, maybe it will work in the few shot. And again, there's too many to enumerate. Just highlighting one that was presented in ACL 2 days ago by people from the NLP group in Tel Aviv University for a few shot extracted question answering. It's called Splinter. You can check it out. So in a sense, very quickly, people realized that maybe it's not the case that there's like one pre-training method for all downstream NLP tasks, but it does seem like people nowadays, when they try to solve an NLP task, they ask themselves, well, can I design some pre-training method that will be useful for that? And this has led to a proliferation of many pre-training methods, many models that are available on Hugging Face and so on. Okay. So just as a slight detour, I just want to point out that this means that there is this implicit consensus that in some sense transformers work. And if we want to tackle new NLP tasks, maybe we don't really need to do anything about the model. We just need to change the data. And we've been working a lot on like how to represent the data such that existing architectures work. I mean, I'm kind of like waiting, like what's next? What's going to be the next transformer? I see people talking about, that transformers kind of like don't need inductive bias and they quickly learn to do what needs to be done based on the data. I'm kind of skeptic and kind of like looking forward to what will be the next transformer. But for now, this is where we are. And given all this, this means that we need methods to generate data automatically, both if we want to kind of like understand the abilities of our pre-trained models, kind of like realize what are their abilities, what things they capture, what things they do not capture, and also maybe to inject skills to language models that are not captured by the pre-training process. Pre-training is mostly about, some denoising, some mass language modeling objective, and maybe some skills are not captured by that, and maybe we would like to inject that somehow. And there are multiple ways by which you can think about getting data for generating data automatically. One very natural way is to think about the web. Maybe the web, we pre-train our models on a lot of data, but maybe some subset of the web that is underrepresented in the data that the pre-trained model was trained on exists. And if we just pre-train on that, then that will be better. So the web is represented by Wikipedia here, just as a joke that NLP focuses a lot on Wikipedia nowadays. But you can imagine that there are some things that are exists on the web, but are underrepresented in the training data, and maybe we can just use that. Another approach is to generate data from models. So you can imagine maybe annotating some data and training some generative model to generate examples and somehow generate data automatically from models. Not going to talk a lot about that, but what I do want to focus on more in this talk, particularly, is that we can maybe generate data automatically by using meaning representations. So as we all know, in the past, people use meaning representations a lot. Someone's knocking at the door. I'm sorry. Really sorry, there was relentless knocking. So people in the past I've been working a lot on meaning representations. We have all these linguistic theories where we learn something about the structure of the language. We know that language has structure and that there are relations between various parts of the sentence. And we use these meaning representations as inputs to our model or as auxiliary tasks to kind of like steer the model towards specific solutions that we would like it to have. But as time went by, the role of meaning representations kind of like slightly decreased a lot, since it seemed that these pre-trained models capture a lot of the information in these meaning representations. But recently, it seems that these meaning representations can be useful, not as inputs to the model, but as ways to generate data. So this is in some sense like revenge of the MERS, like they're coming back for the purpose of data generation. This is what I want to talk about today, like ways by which you can use these meaning representations to generate data. And in the end, I will slightly comment a little bit about how this is like the sim to real of natural language processing, how we can use synthetic data from models or from meaning representations to kind of like bridge the gap between the text that we have and the text that we don't have. Okay, so I will talk about 3 works from my group, very, very recent works. None of them is published, so this is the first time I'm talking about them. Hopefully you like it. And the first will be about using a meaning representation called QDMR that we proposed a year ago. And we'll show how we can use QDMR to automatically generate these evaluation sets that check whether question answering models are robust to various perturbations related to reasoning. So that will be most of my talk. And then I will talk a little bit more briefly about how you can improve the reasoning skills of your model by generating synthetic data from tables on the web and the grammar. And last, I will talk about how you can generate data from synchronous context-free grammar in order to solve a problem in semantic parsing or improve the state of affairs in a problem called compositional generalization in semantic parsing. And all of those basically are about how we can generate data automatically from meaning representations in order to solve problems that we have for real-world text. Okay, so let's start. The first work was led by my student Mo and in collaboration with Tomer, and it's called Break, Perturb, Build: Automatic Perturbation of Reasoning Path Through Question Composition. And the starting point of this is something that I've heard a lot in this conference, which is the fact that the evaluation in natural language processing is in a crisis. We know that we get human level performance on test set that are sampled from the same data distribution as the training set. And we know that when we play around with these models, very, very quickly we realize that they're not actually performing as well as humans, and that there are various artifacts and caveats and so on. And there's been a lot of work on trying to think on how to evaluate this. And one line of work has been talking about generating perturbations to examples. So given an example, you might want to test not only if you're successful on that example, but also on nearby examples, small perturbations to that example that somehow are meaningful with respect to the label. So there was work by Kaushik et al. In 2020, where they had annotators take a sentence like, from the first moment I felt bored, which has a negative sentiment, and they asked annotators to change it to something that is positive. So from the first moment I felt absorbed. And similarly, there was work by Gardner et al. That proposed contrast sets, where here, for example, given 2 images and a statement, you have to say if the statement is true with respect to the images. And here it's true, but if you change dogs to cats or 2 to 3, then the label changes. But the issue with these approaches is that they are expensive. You need annotators to actually do it. And this has resulted in some interest in if we can generate these evaluation sets basically automatically. So in this work, we show that by using a meaning representation called QDMR, we can fully automatically create examples that are reasoning-focused perturbations for cases where you have a complex question answering, questions that require some reasoning. So here's an example. Let's say that you have the sentence, which gallery was founded later, Hugh Donahue or Art Euphoric, then you have this QDMR decomposition. So what is a QDMR decomposition? Well, it's a sequence of steps, and each one of them is phrased in natural language, and every step also corresponds to a single logical operation. And once you have that, once you have this sequence of steps, each one is a single reasoning operation, well, it's very easy to manipulate. You can imagine various manipulation you can apply on this decomposition. For example, you can delete the last two steps, and then this should correspond to when was the Hugh Donahue gallery founded, or you can change larger to smaller, and so on. So the point is, this gives you a lot of control. Now you have control over what type of data you're going to generate, and we're going to use this framework to automatically create these contrast sets that I described before. So here's one slide to pay attention because this is the entire thing. We focus on the reading comprehension problem, though it's more general. I will say something a little bit about that in a bit. We get a question, some text, and an answer from the development set as input. And now we're going to generate new examples. How are we going to generate new examples? Well, we're going to use a QDMR parser to parse the question to this structure, QDMR structure. And we do that by training on the data set that we presented last year called Break, and it's a BART-based model, as you can see. Then we're going to apply rule-based perturbations. We're going to take these decompositions, and it's very easy to perturb them using just rules, manually written rules. And then for all these perturbations, we're going to generate new questions. And we're going to have a question generation model that takes a decomposition and generates a question. And it's trained on the same data set, just in reverse. The inputs are outputs and vice versa. So now we have new questions using this process. And the only thing that remains is to find the new answer to this new question. So actually finding the new answer is non-trivial, but I'm not going to talk a lot about that. It requires some combination of rules and the reading comprehension model that is based on BERT. Okay, so this is the entire thing. Let's look at an example. So this is an example from HotpotoA, which is a reading comprehension data set focused on reasoning. And you have this question, how many novels are there in some series? And the QDMR structure is this. It has 3 steps, the last of which is counting. And we apply this rule-based perturbation that asks if the number, the count, is 23. And then we generate a new question, which is if Shadows in Flight is the 10th novel in a series of 23 novels. So this is the new question. And we can automatically compute the answer to the question because we know that the answer is 15, and we know that we created this new thing with 23, so the answer must be no. Okay, so just a few observations about this pipeline. First, notice that when we generate new questions, this is completely independent of the context. So this can be applied for question answering over tables, over images, over videos. We generate new questions just from the old question without any reference to the context. So in this case, we apply it over reading comprehension, but it can also be applied in other modalities. The second thing to notice, which is interesting, is that this pipeline is based on a bunch of models. One of them is a QDMR parser. The other is a question generator. And the last one is a reading comprehension model. And we're at a point that these things are good enough such that this works, as I will show later. And we should expect that as time goes by, these models will improve, we will be better at these tasks, and therefore this model will produce more and more accurate examples. And the last thing to notice is that these rules, the rule library, those perturbations that we create are just a function of our expectation. So if we think that our models should be robust to some reasoning ability, we should write perturbations that correspond to these abilities. And again, as our models improve and as our expectations from our models expand, we should increase and expand this rule library to capture more and more things. So this is not to read. This is the entire, these are all the rules, examples for all of the rules. So it's just 7 rules that are targeted towards the types of reasoning skills that are frequent in benchmarks that we have nowadays. Okay, so let's see how this works. We run this pipeline over 3 data sets that involve reasoning, DROP, HotpotoA, and IIRC. And we see that we are able to generate examples for most of the data. So this is for how many examples were we able to generate contrast sets. So we were able to generate at least 1 more example that examines and tests whether the model can reason with respect to neighboring examples. And this is the accuracy of the process. So we take 200 to 500 examples for every perturbation and for every transformation. And we ask Amazon Mechanical Turk workers to annotate whether the example is correct, whether the question and the answer and the context are actually correct. And as you can see, accuracy is very, very high. It's over 85%. If you want higher than that, then you can just add a task of verification, and that's much cheaper than generating these examples from scratch. Okay, so I don't have a lot of time, so I will talk quickly about the results. And basically, we can see that models are not robust. Maybe you're not going to be surprised with respect to various perturbations to reasoning. For example, there are 2 models represented here. One is a specialized model that it's like BERT fine-tuned on HotpotoA, and this is unified QA, which is a more generic question answering model that was fine-tuned on HotpotoA. And we can see a large drop in performance compared to the development set when we move to the contrast sets, and also very low consistency, which is for how many examples we get the entire set correctly, both the original example and all of the neighbors. But we can also see that unified QA is slightly better in terms of its robustness compared to the specialized model that was specific just for HotpotoA. And we get a similar picture also for DROP and so on. And one interesting thing about this is that because we have a lot of control, because we know exactly for each example what is the perturbation that was applied, we can kind of check how do models do with respect to particular perturbations. So you can get very interesting analyses. For example, unified QA models on DROP do very poorly on arithmetic operations. And kind of like specialized models also suffer a drop when you change the arithmetic operations. But conversely, if you look at the prune step operation that takes a long sequence of steps and just makes it shorter, we see that the specialized model, TASE, is really not robust. Performance drops by a lot. But unified QA, which is a very general purpose model, doesn't really care that the questions are shorter. It actually does just as well and even slightly better on shorter questions. Okay. And this is it more or less about that. I just want to point out that this is not just us. And there's a lot of papers coming out in the huge pipeline of papers that we all see that generate contrast sets automatically from all kinds of meaning representations. So there's been papers on generating data from syntactic parsers, from AMR, from scene graphs, and from SRL. And the differences are less important than the point, which is a lot of people are using meaning representations in order to generate data in a controlled manner. Okay, so that's it about this part. And then the next 2 parts will be slightly more brief. And in the first part of the remaining talk is not about evaluation, but actually about improving the performance of models that do reasoning. So can we actually make our models more robust to reasoning and do better for various reasoning skills? And this is work with Ori and Alon. Alon is my alumni now and Ori my student, where we try to use tables and grammars to automatically generate data that will generalize to natural language text. Okay. So just as I said, we know that there are caveats and that pre-trained language models don't really do well for in tasks that require kind of like symbolic operations like multi-hop reasoning, numerical, and temporal reasoning. And the idea that we had is very, very simple. Tables are very abundant on the web. And they're very, very diverse. They cover a lot of different topics. For example, they cover movies, They cover, I don't know, launches of missiles, and even they cover tourist attractions in Israel. I didn't know that people visit in the Jerusalem Biblical Zoo more than Masada, but whatever. And they have a lot of structures. So we know that some columns, it's easy to figure out that some columns are numbers, some columns are dates. And it seems that we can use these tables along with some simple grammar to automatically generate data that looks like reading comprehension. And maybe this will allow us to kind of like inject reasoning skills into pre-trained language models. So just in one slide, how does that work? Let's say we have a table. Again, you can think of it as just a context-free grammar where you generate data in the following way. You pick your root symbol, which corresponds to some reasoning skill that you would like to inject into your pre-trained language model. Let's say it's numerical comparison. Then you sample a template for that particular reasoning skill. Maybe there's like 3 or something like that for each reasoning skill. And now you populate the variables in the template using the values from the table. So here the columns and the values in red are filled by this column round and QF and QFR. And this column attendance is numerical, and you fill out the attendance column, and you fill out also some operators. So now you have a question. You can also use templates to generate the context. The attendance in R3 was 16,000 and so on and so on. And because it's a table, you can compute the answer automatically. It's very easy to just navigate the table and find the answer automatically using the knowledge that you have about the question. So the point is that you can generate a lot of synthetic data, and the question is whether this synthetic data will be useful and will transfer to actual real-life reading comprehension data sets. Okay. So again, this is not to read, but the point is this is the entire grammar in a sense. So this is everything. It's not very hard to write this. It's like 40 rules or something like that. And it encompasses a bunch of reasoning skills that are representative of what's in the literature: composition, conjunction, quantifiers, and so on and so on. Okay, and you can generate a lot of data from that. We didn't have to work very hard to get like 5 million of these reading comprehension examples from a lot of tables, from a lot of Wikipedia pages, and the vocabulary is very diverse. You can generate 10 times more than that if you would like to. And now that you have all this data to train, and the way we do that is we take a T5 model and just train this on these examples. For every question and context pair, you generate the input in the usual fashion, and you kind of like auto-regressively generate the answer using maximum likelihood. And to do that, the model needs to learn to reason. And you have to decide how to do this. So you need to do multitask training. As I said, there's like a bunch of reasoning skills. Maybe I'm just, for the sake of time, I'm not going to talk much about that, but you need to decide how you sample which skills to pre-train your model on. And it turns out that it's better not just to uniformly sample a skill, but actually kind of like estimate which skills are missing from your model and sample more from skills with high error, or sample more from skills that are kind of like improving quickly. And you can see the paper if you want the details of training. And in the end, you have a pre-trained model for reasoning. And then you can fine tune on your downstream data set and see whether this is better. And just one slide about the results. Well, we see across 3 different reading comprehension data sets that involve reasoning that this substantially improves performance. And specifically, it really improves performance on questions that require reasoning and doesn't really affect performance on questions that do not. So there's no like catastrophic forgetting or something like that. Okay, so this was the second part where we again use semi-structured tables in a grammar to generate synthetic data, and this generalizes to reading comprehension data sets. How much time I have? I'm not sure when I started.
You have you can take 5 more minutes and then.
Well, like, so how much time from now?
5 more minutes from now.
Okay, cool. So I'll do this relatively briefly. So the last part is about semantic parsing and the problem of compositional generalization in semantic parsing. This is work with Inbar and Jonathan, my students. So semantic parsing, if you don't know, is the task of mapping some utterance questions to some formal language such that when you execute it, you get the right answer. Here it's SQL. And something that people have been noticing, and people in general have been really interested in generalizing to out of distribution, to distributions that are different from the training set. And one particular type of that is compositional generalization, where at test time, you see examples that are new structures, but they're composed of parts that you saw at training time. And people have noticed that sequence models are very bad at this. Training data in semantic parsing is very expensive, and you have very little data. And if you just train on this little data, the solution that the model chooses is not a compositional one. It doesn't generalize to new compositions. So there's been a lot of work on compositional generalization in the last year. And in 10 seconds, the state of affairs is that standard models like T5, even though they do very well in general, they're not great at compositional generalization, but they're very, very general, and very kind of like tailored models that are specific and kind of like build trees in a very compositional manner do very well in terms of compositional generalization, but they're not very general. And there's been a lot of work also. This work is under this line of trying to see if we can fix the model, but change the data, just generate data that is useful for compositional generalization. So in this work, what we do is we generate data from a synchronous context-free grammar. I'll go over this quickly for the sake of time. Basically, you have a grammar that automatically generates in parallel both programs and text. So here this grammar generates the sentence, show me hotels with at least 4 stars, and it corresponds to some program that you execute on a database. And again, because it's completely synthetic, you can generate infinite data from that. And people have shown that by generating a lot of data that is synthetic, you can improve your IID generalization with respect to real data, real semantic parsing data. And this is a new thing. It's a surprising and new thing. And it's mostly because of the progress in pre-trained language models. Before pre-trained language models, you would not generalize from synthetic data to real data. But now it seems that you do to some extent. So in this work, what we show basically is because you have a synchronous context-free grammar, you have a lot of control over the data that you generate. And our hypothesis was that if we generate a lot of structures, then compositional generalization should improve. So if you uniformly sample from your grammar, you will get a lot of sentences, a lot of utterances that look very similar. How many books are there? How many songs? How many hotels? And a few others. But if you kind of like look in your synchronous context-free grammar and make sure that you actually generate a lot of structures, then you get a data set that is much more representative of the different structures. And this should help the model kind of identify the overlapping parts across examples and compositionally generalize. So this is what we do. We generate a lot of data using some framework that I'm not going to talk about right now. And we compare the difference when we generate just at random or when we kind of like make sure that the data set has many, many structures. And we take a T5 model again, train on the synthetic data, and then fine tune on the very, very small target task. And assess compositional generalization, which means that we check whether we generalize to new compositions that we have never seen in the past. And these are the results. Let's just focus on a few things. First, you see that as you generate more data at random, not with any particular mechanism, compositional generalization improves from 20 when you have 0 synthetic data to almost 40 when you have 1 million examples. But if you generate your data and make sure to generate it in a way that it's uniform across structures, you already get 41 points after generating just 5,000 examples. So 200 times less data, and you get roughly the same result. And again, just like in other papers, we show that this also improves generalization in the IID case. Okay, so just to wrap up, because I know I'm almost over, two slides of reflections. So there's a lot of work, very interesting work, and I also work on it, on kind of like integrating symbolic representations very tightly with transformers by changing their attention and kind of like constraining their attention to behave in a certain way. And this is very, very interesting and also successful, but it comes at a price to generality. It's not always possible to do that for all languages. It's not always possible to do that in all domains, and it's not also always possible to do it in all tasks. And you cannot like underestimate the Hugging Face effect, right? Like the fact that the entire community is kind of working using the same models and makes progress together with the same framework or using the same rules is quite effective. And having one architecture is quite useful for that. And symbolic representations are kind of like a powerful tool for us to generate data in a controlled way and kind of like steer our models towards particular properties. And the second reflection and last reflection is that, maybe you would say, why do we need all this synthetic data? Why can't we just like have robots that kind of like roam the streets and kind of like try to predict in every second what will happen next, both visually and in language. And then we really wouldn't need anything except for that and everything will work fine. Well, the problem is that this is expensive. And this is why sim to real is like a very successful paradigm in robotics. And in a sense, what we're doing here is also, it's like sim to real in the NLP world, where we're saying, well, there are some texts that are just like do not occur on the web, and we're trying to generate them synthetically. And the progress that has happened in pre-trained language models in the past years has made us come to the point where this synthetic data actually is able to bridge the gap and allow us to succeed also for real natural language. Yeah, so that's it. And I want to thank my collaborators. And if we have time for questions, I'd be happy to take them.